This program will provide participants with an introduction to plastics processing and an explanation of some of the injection molding parameters involved in the molding process. At the end of this program, viewers will be able to describe the molding process and explain what happens to the plastic during the process. Identify the phases of the process and the molding parameters involved in each phase. Describe procedures needed to develop optimum molding parameters. Identify frequently encountered molding problems and the troubleshooting methods used to eliminate the problem. Injection molding is a process by which the plastic is melted and injected into a mold cavity. Once the melted material is in the mold, it is cooled to a shape that reflects the form of the cavity. The resulting form is a finished part requiring no additional work prior to assembly, and in most cases is the finished product. Many details, such as bosses, ribs, and screw threads, can be formed during the one-step injection molding process. Thermoplastics undergo a physical change when exposed to heat. As these plastics are heated, they melt. Plastics like polyethylene, polypropylene, ABS, styrene, and polycarbonate soften as they are heated. There is a wide temperature range in which these materials will melt without degrading. Nylon, PBT, PET, and acetal do not soften as they are heated and experience little or no change as they reach their melting temperature. However, once they reach their melting point, they melt very quickly. Therefore, they are said to have a narrow melting range. Degradation occurs faster in these materials as any plastic degrades as it reaches the high end of its melting range. The greatest benefit of thermoplastics is that they can be remelted many times with minimal degradation or loss of properties. Another category of plastics called thermosets will change both physically and chemically when heated. Since a chemical change has taken place, a thermoset cannot be resoftened by reheating, and therefore cannot be reused. Thermosetting materials are used for long-lived products, which must withstand high temperatures. Plastic resins require preparation prior to processing. Materials must be carefully checked for consistency and for foreign materials such as dirt, paper, and other plastics. In all cases, it is extremely important to properly identify and mark plastic containers to ensure correct usage. Visually check the plastic pellets before they are put in the machine and notify your supervisor if the material appears to be contaminated in any way. In most cases, dryers are used to reduce the moisture content of the plastic resin to ensure proper processing. Moisture has an adverse effect on plastics. If the resin is processed without removing moisture, cosmetic defects will occur. Moisture can also reduce the physical characteristics of the molded part, such as strength and impact resistance. To remove the moisture in a plastic, a desiccant-type dryer is used. A desiccant dryer works by passing hot air through a desiccant bed, which traps the moisture. To ensure that a plastic material has been properly dried, a dew meter can be used to check the dew point of the circulating air. Resin manufacturers supply the recommended drying time, temperature, and dew point for each type of resin. The injection molding process consists of 3 phases of operation: plastication, injection and packing, cooling. In the following section, we will discuss how to determine the optimum molding parameters for each phase of operation. As always, it's a good idea to refer to the material supplier's information when setting up your machine's parameters. The first stage of processing is plastication, or melting of the plastic material. When selecting barrel temperature settings, refer to the lowest processing temperature that the material supplier has recommended. Molding at a low temperature results in a faster cycle time and reduces the chance for material degradation. Lower processing temperatures require higher injection pressure to fill the mold. Products molded at lower processing temperatures and slower screw speeds tend to have better molded-in properties. Heat profile settings along the barrel determine how the plastic will melt. Plastics like polyethylene, polypropylene, ABS, and PVC can be set up with the lowest temperature in the feed zone and the highest temperature in the metering zone. This is called a forward profile and is the most common profile used in injection molding operations. For nylon, acetal, PET, and PBT, the zone temperatures are fairly constant, creating what is called a straight profile. A reverse profile may be used for materials which have a tendency to drool, such as nylon. In a reverse profile, the lowest temperature is in the metering zone and the highest in the feed zone. The barrel temperatures will be lower than the actual melt temperatures of the plastic. 70 to 90% of the heat required to melt the material comes from the shearing action between the screw and barrel. Therefore, screw speed is a critical parameter for controlling melt temperature. Screw speed determines the rate at which the plastic pellets melt. It is necessary to maintain a slow, steady, consistent speed to evenly melt the material. To determine the correct screw speed, refer to the processing information supplied by the material manufacturer. It is important to use the lowest possible setting that will allow for uniform melting. A high screw speed may overheat and degrade the plastic material. This will cause dimensional problems as well as a reduction in the physical properties of the material. Screw back pressure causes the screw to make more revolutions. These additional revolutions create more shear heat, which can cause material degradation. Little or no back pressure should be used with glass or mica-filled materials. Back pressure breaks up the filler, which reduces molded part quality. Increased back pressure also accelerates wear on the screw and barrel. For materials using a color concentrate, back pressure can be used to assist in dispersing and mixing the colorant more evenly. Extra back pressure can be used for screws with smaller lengths over diameter ratios. Many older machines have small L/D ratios, such as 15:1. However, screws with higher L/D ratios require very little back pressure, since more mixing takes place. After screw recovery, suckback is used to prevent the nozzle from drooling. Too much suckback may cause splay or bubbles on clear molded parts. Several molding parameters directly influence the injection of plastic. The melt cushion is the buildup of melted plastic which remains at the front of the screw. When injection molding, always use a melt cushion of 1/8 to 1/4 of an inch to allow the part to pack out evenly. A process without a melt cushion is a process out of control. Be cautious, however, as pressure loss may result if the cushion is greater than 1/4 of an inch and the part will not mold consistently. Injection speed is a key processing parameter of the injection phase. Injection speed is controlled by the amount of hydraulic oil pumped into the hydraulic cylinder piston. Older machines have only a simple flow control valve to regulate the flow of hydraulic oil. Opening the valve allows more oil to enter the piston at a faster rate, and thus the plastic is injected faster. For materials that flow with some difficulty, it is recommended to use full injection velocity, or 75 to 100% of the available injection velocity. For molding plastics that flow more readily, it is recommended to start at 50% of the available injection velocity and slowly work up as needed. More advanced machines can control multiple stages of injection velocity. For example, a process may demand a slow speed to fill the sprue and runner, a faster speed to fill the part, and a slower speed just before the part is completely filled. Later model molding machines allow for better control of the process, and as a result, yield less part-to-part variation and better part performance. Pressure is created by a resistance to flow. Pressure settings on the machine determine and regulate this resistance. To establish first-stage injection pressure, raise the pressure to a point where the part fills out without any packing. The screw will come forward and stop as it reaches the melt cushion. At this point, second-stage pressure comes on to allow the melt cushion to pack out the part. A molding machine's hydraulic design dictates your molding process. Older machines usually have a combination hydraulic pump. This pump includes a high-volume, low-pressure pump and a low-volume, high-pressure pump. The high-volume pump allows for fast, steady forward movement of the screw. The low-volume pump handles the packing of the part. The high-volume pump consumes more energy than the low-volume pump. Therefore, it is best to switch over to the low-volume pump as soon as possible to reduce energy consumption. More energy is conserved by reducing the first stage time as opposed to reducing the cooling time. The more advanced molding machines can control 5 or more pressure settings. This degree of control can greatly improve final molded part quality. Injection time is the amount of time that the screw remains forward. Injection time is controlled by the rate of hydraulic oil being pumped into the injection cylinder piston. Assuming a machine has only a first and second stage, the first stage is the amount of time it takes to fill the part. The second stage is the time required for the gate to freeze off. On a multiple stage injection, the last stage is usually the packing stage. During the final stage of cooling, mold temperature directly affects product dimensions and stability. An even distribution of water lines is needed to accurately control the process and part-to-part uniformity. A hot mold produces parts with less stress, higher gloss, and usually requires less clamp tonnage. The cycle time of the part will be longer. Depending on the part thickness and application, this may or may not be significant. Engineering resins require hot molds from 150 to 220 degrees Fahrenheit. Specialty resins require hot molds in excess of 300 degrees Fahrenheit. A cold mold produces parts with a dull surface appearance and more molded in stress. Cold molds require more clamp tonnage, but produce parts at a faster cycle time. Cold molds are used for commodity-type resins, which typically run at about 70 degrees Fahrenheit or less. In this section, we will discuss problems frequently encountered during machine operation and the troubleshooting procedures used to solve them. First, it is important to determine the root cause, and then take the necessary corrective action to eliminate the problem. You should understand that every quality and processing problem has a number of viable solutions, and more than one corrective action may be required. In all cases, try the obvious and simple things first. Allow some time, or a few shots, for a change to take effect. It is important to realize that whenever the barrel temperatures, screw speed, or mold temperature is adjusted, the effect may not be seen for 30 to 45 minutes. On the other hand, results of changes to pressure, speed, or position can be seen almost immediately. If clamp tonnage is too low to keep the mold closed during injection, flash or intermittent flash may result. Check the clamp tonnage and make any adjustments necessary. Keep in mind that a low clamp tonnage requires less energy and causes less machine and mold wear. It may be necessary to reduce injection pressure, injection speed, or material temperature in order to fully eliminate the problem. Plastic material that is not properly dried will flash. An improperly dried material will flow more. This will reduce the packing pressure and may also produce brittle parts. Check the dryers to be sure they're working properly. When experiencing short shots, check to see if the shot size is set at 20 to 80% of the rated capacity. If not, make the necessary adjustments and see if that eliminates the problem. You may have to increase injection pressure, injection speed, injection time, or material temperature to completely fill out the part. Sink marks may be caused by a number of processing oversights. Assuming the sink is not the result of a poor part or mold design, additional packing may be required to fix the problem. Check the shot size first to make sure that it is sufficient to fill the part. Injection pressure or injection time may have to be increased to allow for more packing. If the mold temperature is too high, parts may begin sticking in the mold. Other possible causes include high injection pressure, high material temperature, and corrosion of the mold surface. In some cases, undercuts are machined into the mold to keep the part on the appropriate side. Black specks or streaking in clear material is caused by material contamination. Purging of the barrel after using a dark material will help to avoid contamination problems. To completely purge the system, pull the screw and clean the screw and barrel by hand. Ultimately, it is your responsibility not only to diagnose the problem, but to solve the problem. Be sure to record any change and the reason for the change on the process setup sheet in case the problem arises again. In this program, we have seen a description of the molding process and what happens to the plastic during the operation. Some of the molding parameters in each phase of the molding process. Procedures for determining optimum molding parameters. Frequently encountered molding problems and the troubleshooting techniques used to solve molded part problems.